manga muchizviziva here kuti maxutra ine mitsetse yakakurisisa. Vari kutengesa zvakachipisisa kumaxutra inhaka yedu. Maxutra unoziva kutenga, tenga unanzolelo pachindevere, tenga nehungwaru pachikaranga. Munhu anotenga zvakangwara kunanga pamaxutra woona bhodhi riripo wobva waterera zvizhinji pamumanzi. Maxutra nhaka yeZimbabwe.
Right, so we come back again after a very long time. You know, Corona lockdown came and it changed a lot of dynamics of operations of everyone in the whole world. But the subject I'm bringing today is, the subject that affects everyone. It's a practical subject. We are going to talk about the structure of the power system. The structure of the power system. What is a power system? What does it do? Why do we need it? And then what are the expectations of its performance? What are the shortfalls? What causes the shortfalls of the power system performance expectations? And what do we use to measure its performance? So those are the subjects that we are going to be talking. We are not going to cover everything at one go, but for today we are going to talk about the structure of the power system at a high level for everyone to understand. By everyone, I mean you don't need to be technical to understand what I wanted to present here. Right, so what do we start with? We start with a very basic rule, which I want to believe that 90% of the people or 80% of the adults, they know that rule, that energy cannot be created or cannot be lost. You can only change it from one form to another. We want to start from there. So, what it means is we should have the human needs requires energy, right? So we must create energy from somewhere. We know that we are going to destroy, we are not going to create, but we are going to change from one form to another, right? That is the rule which is there. So, at the point of where energy is converted for us, of interest sake, in the context of a power system, we have what is called generating stations, power generating stations, right? And then at the usage point, we have conversion from electrical to various types of energy. For example, here in this room like now, we have got light energy. So electrical is being converted to light energy. We have got cameras that are using batteries. We have got television sets. We have got computers. And in the industry, we have got motors running, changing electrical energy into motion, kinetic energy of rotating parts, and so there's so much of things. So it means we've got a generating station and we've got the point where the power is used. Now, we need something in between the power station and the load center, or where the power, what I'm calling the load center is where the power is being consumed. What I'm calling the generating station is where the power is generated, or where the energy is converted from one form to electrical. And then the load center is where electrical is converted to another form of energy. Remember, we're just converting energy here. Right. So we've got two tabs that I'm going to concentrate on. We've got conventional sources, we've got non-conventional sources. Conventional sources are those sources that we already know from time immemorial, like thermal power stations and hydro power stations, micro hydro. Of course, they are recent, but they are a bit long. And then we've got non-conventional. Non-conventional, we're talking about renewable energy sources mostly, solar photovoltaic, solar thermals, and so forth, biogas, you know. But with time, as time goes on, we will narrow our focus to solar photovoltaic and solar thermal. Those seem to be on a downward trend in terms of economics and the financing of such projects. So those are what we are going to be measuring on as we go on. Then on the conventional side, we're going to measure on thermal and hydro. We're trying to understand their shortcomings and their reliability, their stability, you know, their economic operation, and so forth like that. Right. So we start with the hydro power station. So for hydro power station, what do we need first? What form of energy is available at a hydro power station? We have water. Water, what does water have at the hydro power station? It has got what is called potential energy, right? It has got potential energy due to its elevation from the reference horizontal ground, right? Or the reference from the point where it is going to start its job, which is the turbine intake point of that water. And the difference between the intake point or the turbine point and where the water is coming from is often referred to as the head. So the bigger the head, the greater the potential energy of such body of water. So already we can see that the requirement or for a possibility of having a hydropower station, one of the key requirements is height from the ground. I can give you an example here of domestic water tanks. You know, if you want water to come inside the house, by natural forces, it means your tank has to be elevated from the least point of the tap. Otherwise, if they are at the same point, water will not come out from the tank to the tap. But if the tap is below the tank, then water will flow down by natural gravitational force. So in other words, there's an issue of gravity here. Gravity, which is called acceleration due to gravity, is constant. Mass of water is constant. What we can only change is the height, which is the head, from the turbine point to the intake point, what is called as the intake gates, where water comes through from the dam, then it flows down to the turbine point. It will go through towards the generator, it will go through what is called the spiral casing and so forth. We are not worried about those details for now. Right. Now, if our source of energy, the first source of energy is water, it means if there is no water, there is no energy to talk about. There's nothing to convert from. One. We will use that point later on. Well, let's shift to the thermal power station. Our source of energy there, because it's thermal, we know we are going to have some heat of some sort. So we want something that we can heat or what we can burn to generate heat so that we can boil water in the boiler tubes, so that that boiling water turns into steam, high pressure steam. That is what will go and heat the turbine such that the turbine will rotate, and then as it rotates, it's coupled to the converter which converts that motion of the turbine to electrical. In other words, that's where the generator is coupled. The generator is just a converter which converts mechanical rotating energy to electrical energy. The conversion process of the generator at the thermal, generator at the hydro are the same principles. They both have a rotor and a stator. The rotor for magnetism, then the stator for the final production of voltage and current that is then taken somewhere. Right? How is it taken somewhere? From the generating stations, we now need an evacuation route. What I'm calling an evacuation route is the road. We need the road to take this power from the generating station to where it's supposed to be used. Just like a person in a bus traveling from point A to B, we need a bus and a road for that person to move. So here our product that we want to move is electricity or electrical energy. That is what we want to move. We are not going to go into how it actually is composed of, but just for now we are bulking it to electrical energy. That is what we want to use. Right. So we have got a series of components or equipment or plant and equipment in between the load center and the generating station. Right. This equipment is composed of substations, transmission lines, and within the substation we have got plant and equipment again performing various functions, but the overall objective of these transmission lines and plant and equipment within a substation are to transmit and sub-transmit and distribute the energy, the electrical energy. I can give just a few examples of what we find in a substation or what is expected to find in a substation or a switching station. We expect to find transformers, reactors, capacitors, static VAR compensators, fixed devices, flexible AC transmission systems. Right. We all need all these just for the purpose of transmitting electrical power from the generating station to the load center. However, where there is motion, there is resistance. So as this movement happens, we are going to have power losses along the way. We will need that later on in this series that we've just started. At the generators, what I've also left, there are a lot other control systems, instrumentation that is used within the power station. We'll get to those in later sections of this series. There are also generator unit transformers, there are circuit breakers, there are mechanical cooling systems of generators, there are control systems of movement of water that is approaching the turbine. How much water is hitting the turbine is also controlled, which in other ways they are what are called guide vents, they are what is called excitation controllers, they are what is called power system stabilizers, they are what is called automatic voltage regulators. We'll get down to that. For now, not necessary for the level that we want to deal with. Right. So we have taken our power from the generator station, thermal or hydro, or non-conventional. We have moved it. We are now at a point where we want to transmit it. There are conditions that we are supposed to do. To avoid that which I have called power losses, we are supposed to transmit our power or to send our power to the load sender at high voltage and low current, because these losses, they are as a result of current moving through a resistor, and the losses are proportional to the to the current squared. Therefore, reducing the current helps in reducing these losses. Hence, you see that power transmission is associated with what is seen as very big pylons, very big towers, and a small conductor at the top, but they are very high. They are very high up there because the voltage there is too high, such that there are safety considerations. It's also another subject that we will talk about, safety, when we are dealing with the electricity. It's very important because life, it cannot be bought. Once it's lost, you can't recover it. So we'll also deal with that in later sections. Right. So we have transmitted our power at that voltage level. Obviously, we are going to pass through a lot of towns, a lot of load centers. So we will need to take it down to usable levels by domestic users, by light industry, by heavy industry. So we have substations located in various load centers for the purposes of manipulating this energy, this power, into usable form at each load center. The power that the TV requires is different from the power that a boiler at some production company requires, or is different from the power that a certain motor may require. Those are different in terms of current magnitude and voltage magnitude. They are different. Therefore, we need substations to manipulate that power into usable forms. So we have possibly what is called sub-transmission. Sub-transmission is just another sub-level of voltage. And then we have what is called distribution. It's another lower level in terms of voltage. And then we take it to domestic users, right? We've talked about this from the generating station to the load. So there are characteristics of power that we need to highlight at this point, because later on we will use that point. It is a rule of thumb that the power that is generated at the generating station should be equal at all times to the power that is consumed at the load center. The total power generated is supposed to be equal to the total power being consumed. Here I will give a very practical example that we often experience for those that grew up in the ghetto areas, mostly in Africa, in developed worlds. I'm not sure if you are quite familiar with that kind of scenario, but in the developing world, that kind of scenario is very popular. You have a power system planning company planning that in this house there's going to be a demand of this much in terms of watts, and then in this house there's going to be a demand. What they would have done, they would have assumed possibly one stove per family, 1, 2 fridges per family, a television set or 2 television sets, and so forth. Then they come up with a demand for a domestic user. But what happens now? 3 families come and live in one house. So, we are going to have 3 stoves in one house. Maybe 6 television sets, or maybe 6 set of fridges. So the load is tripled in that house. Now, at that house, just at that house, we can have a scenario where these people will become aware that if we all try to bake and cook at the same time, what is called a mains circuit breaker will trip. What is it doing? It is tripping because it is overloaded from its capacity. The load that is behind it or downstream it has become more than what it is designed for. So it will trip. So what these people will now do, they will start to call each other because they are in the same house. Ma'am, are you cooking? Can we cook? We are also cooking, so can we at least switch off all our ovens and just cook salsa or just cook rice or just cook this? They will agree in that house and the breaker will not trip as long as they follow that. But these people are in the same house. Let's now take people that are in different towns, but they want to cook at the same time. And for that time, power is not enough. Remember, we've said power consumed is supposed to be equal to power generated. These people, they don't know each other because they're in different towns. So, how are they going to coordinate the communication? No ways. This introduces us to a concept of what are called load dispatch centers or national control centers within many utilities. They are what are called control centers or load dispatch centers. And within these centers, they are equipment and super computers that collects information of that power network to that center, which I am calling the load dispatch center or the national control center. This information at this level will just talk about the total load and the total generation in terms of megawatts. How much is being generated, how much is being used. So it will display that information. To collect data from all generators in that power network and collect all data in terms of how many stoves, how many motors are connected, how much are they consuming, sum it up and then brings the total and it balances these two totals. Firstly, there is an automatic control system which senses these variations that what is being consumed is now more than what is being generated. So this control system or automatic control system, which is called automatic generation control, or in some terms load frequency control, depending on which word you want to use, but its purpose as a control system is to balance load and generation at all times automatically. How does it do that? Because it takes signals from remote terminal units in terms of load, and then takes generation, totals it, see the mismatch, calculates the difference, and establishes the need, whether it needs to rise up generation or to lower generation. It then sends signals to what I initially called a turbine governor control system to say, allow more water to come through so that we can increase our generation, or close the gates a little bit so that we can lower the generation, because people are starting to be sleeping and switching off their stoves and so forth. Therefore, the load is reducing, so we need to reduce the generation as well to keep the frequency at 50 Hz, to keep the system in synchronism. So that is the role of automatic generation control. So it's found at load dispatch centers. Right. But this is a system which has got generators that are able to meet demand at any given time. In other words, the generators that are connected to the system and spinning, or the code reserve and whatever reserves, is sufficient for that particular load. That is the scenario in most developed countries and world. But coming back to the developing world, we will find that the scenario is a bit different now. The generation capacity is usually below the load demand. The absolute figures of the two, the generators are less than the load demand. Right, so what happens? We will have times when everyone is in need of power and needs to be cooking, doing that, and usually this time is the morning and the evening. In the afternoon, yes, but not that much. So you have a spike in the morning, a spike in the evening of demand. Now let's take an example where we have got a power network which is importing power from power markets and from bilateral contracts and from local generation, but it's not sufficient to supply its peak demand. This is when another technique which is meant to save the power network from collapsing in what is called a total blackout or a partial blackout. This technique is the unwanted most technique, sadly being viewed as bad, but it's a good, unavoidable technique, which is called load shedding or load curtailment. Outside the power utilities, it is viewed as an irrational decision, in the sense that it takes out power when one wants to use it. Within the power network owners or operators, it is viewed as a method to save the system from total collapse. At this point, let me give an example of a car that is moving. When a car is moving, I will just give you a few forces and around it. We've got frictional force, between the tire and the tire, and we've got drag force that is coming through the air that it is facing. But to overcome these forces, we've got chemical energy stored in the fuel that is burnt in the engine, and then we've got energy to move forward by a lot of other transmission components that are part of the car, right? If you want to maintain 100 kilometers per hour, it means you're supposed to burn some quantity of fuel for you to do that, because there's frictional force and there's drag force. So if you don't supply fuel, the car will eventually come to a standstill. If you are now going downhill, it means you have to reduce the amount of fuel supply and possibly apply some braking system so that the car maintains 100 kilometers per hour. Otherwise, if you don't do that, the car will run possibly to disintegrating speeds. If you are now going uphill, you need to apply more fuel for you to maintain 100 kilometers per hour, because there is now a component dragging your car backwards, any additional to friction and air drag force, which is now acceleration due to gravity, due to its weight. So it's also being pulled back. There will be a component that is pulling the car backward. Like if you hold a stone and you leave it, it will fall down. That is because of gravitational force. So the car will have a component that is pulling it backward. Otherwise, if you shut it down and leave it in neutral, it will start to roll backwards on its own, even if the engine is shut down. It will actually start to accelerate due to acceleration due to gravity. Right. How is this relating to a power system? We have said we have got a scenario where we have got a power utility A, which is not generating enough to supply all its demand. So at night, everything is balanced. In fact, not just that it balanced, it has got more generation than the load, because people are sleeping. Now around 5, let's say starting from 4, people will start to wake up, turn on their loads, stove, industry will start to run around 6 and so forth. Motors will start to run. So the load will start to pick up. So as it do so, the generator control system, the automatic generation control system, will also sense that load is picking up. So it will allow the generation to also start to pick up what is called spinning reserve. The generation that is already there but not being used, but is part of the generator. For example, to understand that, we are saying if a generator is rated 100 megawatts, but it's rotating but generating 75, it means this generator is already rotating. It can add 25 because that's its capacity, but at this time moment it is taking water just sufficient for conversion to give 75 megawatts. But it can open wide its gates to take more water to generate its maximum, which is 100. So it will gain 25. So it will supply an extra. So if you add generators like that, if you have got 4 of them, it means you will add 100 to the system. Now we'll come to a scenario where we have added, and we've come to the maximum of say 1,500 megawatts, but our load demand is 2,000. But because there's no communication between the industry, domestic clients, and the power utility, the person who is in overall view of the system is the one that is residing at the load dispatch center. So this person now has got a task now of not allowing load to keep on rising so that it matches the 1,500 maximum that the power station's imports are able to supply. What would this person do? It's in two ways: planned and unplanned manual load shedding will have to be activated. Right. Planned is when you have created an operational forecast, short-term operational forecast, where you already know that at around this time I will have a shortfall of this much, so I'm going to remove this load and that load and that load. So you can send a schedule to your customers or clients in time for them to know that on Tuesday or on Wednesday we will not have power from 2 to 8, from 8 to 9 a.m. and then the others will know that we won't have power from 9 to 10, something like that. And then at night everyone will have power, and then maybe around 12 noon everyone will have power, something like that. But there will be times when people will rotate not to have power. This is a planned scenario. But this planned scenario is coming from a mismatch of 1,500 and 2,000 demand. But let's take a scenario where, because of unforeseen reasons, that other generator which is giving 200 megawatts to make the 1,500 develops a fault, a sudden fault, and then it is out of the system because of its protection system, because all these machines will have an intelligent way of protecting themselves from aggressive damage. Just like anything else, even a human body has got that facility where you've got antibodies and so forth to take care of the body of the person. A car has got so many interlocks, control systems to make sure there is no further damage. There are cars that if you go to bumpy road, they will tell you there is no road here, they will stop. So, such kind of things. So even generators have got that kind of facility. If it develops high temperature, maybe because of a bearing failure, it will stop, right? So let's suppose, due to any other fault, the generator is isolated from the system by its protection. Then you have got 1,300 suddenly that you had not forecasted that you will lose. It means then you have what now we are calling an unplanned manual load shedding. Or it can be automatic load shedding. Right. So the difference between those two, we will of course talk about them in other series that are coming. But for now, we are saying we have faced a scenario where we have got a sudden shortfall of 200. Under that circumstance now, the person looking at the system will have to quickly remove the load equivalent to 200 so that it will match the 1,300 now being generated to the 1,300 load. So the other 200 will have to be removed. Under such circumstances, there is no prior warning, because the time that is supposed to happen, remember we said the rule of thumb is generation has to be equal to consumption. Here I can give an example of a small generator, a domestic small generator. If you put on a welding machine and say the generator is balanced, it's running well. If you put another welding machine of the same size, the generator will tell you that now I can't take this, and it will give you a sound that you know this generator is not sounding normally. If you delay removing the other welding machine, the generator will shut down itself. That is the scenario that the power utility or power utilities don't want and wants to avoid, a total blackout. A total blackout is a scenario where all generators are out of the system. One, because it's expensive to restart the power system, because you will need a lot of expensive power to start excitation processes and stuff like that, to start boilers and for thermal and so forth. Right. Therefore, we don't want that kind of scenario, or that kind of scenario is not wanted by any power network operator. So, to avoid that, the 200 will have to be removed immediately. Then after that, then the client will be called to be notified that we have just removed your power, we have cut you off because we have developed a problem somewhere, but maybe the problem, if it is now known that it will take this much, even time, then can be supplied. But otherwise, for today and for now, we are going to end here as an introduction to the practical aspects of power and energy, measuring on the electrical energy. Otherwise, I thank you for watching, and please keep subscribing, keep liking, keep sharing. I mean, the more we know it, the more we suggest the solutions, the more we make the globe a better world to stay. Thank you.
Max Ultra Energy, reliable in solar system. Kazona panex dopako panechieza usazoshamisika kana kuvunduka kazhinji tinogara tichitaura nezva Max Ultra Energy solution. Shasha power ring Max Ultra Energy solution.